This is a topic on conductors part 2, and in this section we are going to discuss a lot of problems and applications based on the chapter or the topic on conductors. So first things first, we will revise what we had learned so far, and the most important things that we had learned so far were the properties of conductors. The very first property of a conductor was that the net field inside conducting material is 0. The second property was the derivation of the first property. If net field is 0, then there is no change in potential, and that gives us the second property, potential at all points inside the conductor is same. That gives rise to the third property. If the potential is same, then the entire conducting surface is equipotential and the field lines fall is not a good word, terminate at or originate from conductors at 90 degrees. So we have a conducting sphere here. This is a conducting sphere. You can assume some ideas, some things about it. It might have a radius r, let's say. This is your sphere and it has a radius r. Now there is some charge outside the sphere, some charge outside the sphere, small q, and there is a charge on the surface of the sphere, that is capital Q. Some charge outside the sphere, small q, and some charge on the surface of the sphere, capital Q. Or let's do something, let's ignore small q for now. We simply assume that there is a charge capital Q on the surface. And right now the charge is uniformly distributed on the entire surface. Uniformly distributed on the entire surface, like a hollow spherical arrangement. So I'll write it here. Charge is uniformly distributed like a hollow spherical arrangement. We have learned the field and potential of hollow spherical arrangement. We'll come back to it in some time, but not right now. So what is happening here is we place another charge small q here. And we know that due to this charge small q, there will be field lines that will pass through the conductor. There will be also field lines that will not pass through the conductor. We are not interested in those field lines, but I am still drawing them. But there will be field lines, these field lines, that are basically passing through the conductor. Now what happens when field lines pass through a conductor? Few simple things. The charges gets pushed, positive charges gets pushed in the direction of the field lines, and the negative charges gets pushed opposite to the direction of field lines. Let me draw another line. So positive charges gets pushed along the field lines, negative charges opposite to the direction of field lines. And what will happen due to these charges? There will be an induced field. There will be an induced field. I have explained this in my previous video. There will be an induced field, the red in color, which will cancel out the original field that is green in color. I want you to see that there is a combination of positive charges on this side, on the left side as you might like to call it, and there is a collection of negative charges on the right side as you might like to call it, right? And then we also have the net charge plus Q that was uniformly distributed. Now what happens when we start looking at the system in a combined view, in a singular view, not as one-on-one? If we look at the system in a combined view, we'll have to see what happens. So there was this scenario, the charge Q, small q, and then there was charge capital Q. There will be a high density of positive charges on this side. And there will be a low density of positive charges on this side. And why is that? In order to see that, we'll have to see the diagram that was the previous diagram, this diagram here, this one. In this diagram, you might see that there are positive charges which are uniformly distributed, again uniformly distributed, and then there are also positive charges that are induced. So we have two kinds of positive charges, and when both positive charges get mixed out, in the lower diagram you will have a high density of positive charges on this side. Whereas if you see on the right side, there are positive charges uniformly distributed, and then there are some negative induced charges. When you mix them up, when they start getting added up, we'll come back. So this is what happens. We have a lower density. We have a low density of positive charges here due to the mixing of plus and minus. But overall charge, I'm writing it here, overall charge on the conducting sphere is still Q. And why is it still Q? Because the induced charges were equal and opposite. Or we can say because the induced charge cancel out. Because the sum of induced charges is 0. Sum of induced charges is 0. So this is going to be the arrangement that is happening. Let me remove this thing from here. Okay, so all right, let me draw this Q here, and let me also draw the center of the sphere. And what is happening at the center now? What is happening at the center now? We know that net field inside a conductor is 0. We know that net field inside a conductor is 0. And how is that happening here? You can see the field due to Q. Let me show it in a different color. The field due to Q is in this direction. This is the field due to Q at point C. E equals to KQ upon R squared, where R is obviously the distance between the center C and point Q. Now the second part, this was field due to Q. Now the second part, field due to capital Q. Now field due to capital Q is very difficult to actually calculate it, but we must have an idea here, a general idea. What does the general idea say? The general idea says that if there is a highly dense arrangement of positive charges on this side and a very low density of positive charges on this side, the overall field must be something in this direction. Overall field must be something in this direction just to make the net field inside the conductor to be equals to 0. So field due to Q will be also KQ upon R squared, but the direction will be opposite. So if let's say this is plus, we can write it minus, or let's okay, well, I'll not confuse you with directions. So the direction of field due to charge Q will be opposite to the direction of field due to charge small q, and that's how the net field inside the conductor will become equals to 0. Now let's talk about field at a certain point, which is obviously not the center. Let me consider this point P. Field at point P. So field at point P, let's say this distance is r dash. Field at point P will be in this direction due to charge small q, and you can very well write the field due to charge small q will be equals to kq upon r dash squared. And again, the field due to the charge on the sphere will cancel out the field due to charge small q. The red line, this red line represents the field due to this non-uniformly distributed charge capital Q. This one here. And why is it in this direction? You can see there is a high density of charges here and there is a low density of charges here. So obviously you will have a direction that is in this way. It's not a very comforting answer, but we know that the net field inside a conductor is 0. So field due to capital Q will also be kq upon r dash squared, but the direction will be opposite. So this was our arrangement, and now we are not trying to find out fields, we are trying to find out something else, that is potential. So the next question becomes, what is let me mark that this was charge Q. So potential at point C due to Q. And you know that it's going to be very simple. If we know the distance, let me draw a different color here, slightly problematic. Okay, if we know the distance was r obviously. The potential at C due to Q becomes equals to kq upon r. Now comes the next problem, potential at C due to capital Q. Now we know that the capital Q is distributed on the surface, although not uniformly. It is an ununiform distribution. You can see that the density here is the density here is high and the density here is low. So we can very easily say that it is a non-uniform distribution. So even though it is a non-uniform distribution, there is something important to understand, that you take any charge, low density, high density, does not matter. You take any charge, all charges are at the same distance from the point C. So the potential at point C simply becomes equals to kq upon r. Now we are at the same question again, and this time we have chosen a different point. We have chosen a point, let's say P. This was the center of the sphere C, the radius of the sphere was r. Now we have chosen a point P, and again the same set of questions, potential at P due to, okay, let me change this was not capital Q, this was small q, and this charge was capital Q. So potential at P due to charge small q, and that was very easy to understand. If you can see the distance, let's say this distance is r dash. So the potential at point P due to charge Q is simply going to be kq upon r dash. Now comes the last and the most important question of this series. Potential at P due to Q. This is the most important question of the series. We have to find out the potential at P due to the capital charge Q that is non-uniformly distributed over the spherical surface. This charge, capital Q. So what are we going to do about is this. We know that the charge arrangement is quite complex. It's very hard to find out directly and then individually each charge and then integrate it. It's very difficult. We are not going to into that. We are applying a shortcut process. Now, what is the shortcut process? The shortcut process involves a basic concept. The basic concept is that the field inside the conductor is equals to 0. And if the field inside the conductor equals to 0, then dV equals to 0. dV means change in potential. dV means change in potential. And if dV means change in potential, we will know or we will understand very easily that Vc becomes equals to Vp. The total potential at C is equals to the total potential at P. Now I have told this to you once, but I will try to do it again here for clarification. The potential at C is due to two charges. The potential at C is due to small q and potential at C is also due to capital Q. And from the last part that we studied, the potential at C due to small q, if you remember that this distance was small r, was kq upon r. And due to capital Q, we know very well that capital Q was the charge on the surface, and all charges on the surface have same distance, that is radius of the sphere. So the potential due to capital Q was kq upon capital R. And we must understand from this concept here that potential at C, total potential at C, Vc total equals to Vp total. And what was the total potential at C? We will get this result from here. The total potential at C was K small q by small r plus K capital Q by capital R. But we don't have to find Vp total. We have to find something else. What have we got to find? We have got to find potential at P due to Q, just this charge. So potential at P is going to be written as, let me move this up a bit, right. So potential at P is going to be written as potential at C, and that is going to be written as kq by small r plus kq by capital R. Now we also know that potential at P can be written as potential due to small charge q plus potential due to capital charge q. Now we know very well what is the potential due to small charge q at point P. At point P, the potential due to small charge q can be simply written as kq upon r dash. Why r dash? Because r dash is the distance from point P to Q. Plus, we don't know about this because the distances are very complex. But what we know is this, that these two terms have equal values. Why do they have equal values? They have equal values simply because of this particular reason, that field inside is 0 and potential at C is equals to potential at P. So if you equate the two values, this value and this value here, you will simply get VQ equals to KQ by R plus K capital Q by capital R minus K small q upon R dash. Okay, so this is a conductor again, the same type of conductor that we have taken in the previous cases. Now I am asking a very important question because for our next topics, this question is very important to answer. The question is simply this: can we have a conductor with charges distributed in its volume. Or should I simply say that can we have a conductor, spherical conductor with charges distributed like this inside the volume? Can we have that? Is it possible at all? And not to mention that it is a conducting sphere, it's a conductor. I'm not talking about non-conducting spheres, I'm just simply talking about the conductors. Can we have this scenario? That is the question. Now, a very important theorem that we have studied in the previous classes comes into play at this point of time, and that important theorem is the Gauss theorem. So, if we take a Gaussian surface, let me draw the charges again because they're hiding behind the diagram. Okay, so if we take a Gaussian surface, this is our Gaussian surface. Gaussian surface, and inside the Gaussian surface, let's say the radius of the Gaussian surface is r, and we know that there is a Gauss law. The Gauss law says that E into 4 pi r squared, that is the total flux, equals to Q enclosed by epsilon naught. This is what Gauss theorem states. This is basically your Gauss theorem. Now it might be already visible to you the problem there. We know that inside the conductor the field is 0. And if field is 0, then the flux through all points on this sphere, will be 0. So we can have flux through surface S, let's call this surface as S, the flux through surface S is 0. So if we come back to our equation here, we know that field is 0, so the flux is 0. So flux is 0, that is Q enclosed by epsilon naught. And what do we get? You get Q enclosed equals to 0. So that answers our question. Let me mark it separately here. Can we have a conductor with charges distributed in its volume? No, of course not. And why not? Because if we consider a conductor with charges distributed in volume, it will be violating the Gauss theorem. And this happens in all conductors. You have to understand what is happening here. Let me move this up. If you take a conductor and if you somehow, I'm not saying there is a way to do it, but if you somehow fill the conductor with charges, by force, by some kind of effort, you fill the conductor with charges, then what is going to happen almost instantaneously, even less than in an instant, is that all these charges will push towards the surface. All the charges that are there in the conductor. Let me remind you again that this is a conductor, not a general sphere. So all these charges will push towards the surface, and within moments, in less than, as I told you, less than moments, you will have charges distributed on the surface of the conductor. You'll have charges distributed on the surface of the conductor, and I want you to show this to you why it works. If you consider a Gauss theorem here and if you consider a Gauss theorem here, both places you have considered a Gaussian surface. Both surfaces have same radius r and r. Over to the left side, your equation is unbalanced. Why is it unbalanced? Because E into 4 pi r squared is equals to Q enclosed by epsilon naught. And we know that E is 0. So it is unbalanced because there is, in this diagram, there is some enclosed charge. So this equation is an unbalanced equation. But over to the right side, E into 4 pi r squared is equals to Q enclosed by epsilon naught is a balanced equation because E is also equals to 0 and Q enclosed is also equals to 0. So you must understand that even if you have a conductor in which charge is distributed in a volume, within moments, within a very small fraction of time, all the charges will push themselves towards the surface and they will be distributed on the surface. So we cannot have a conductor with a charge distributed in its volume. Now we come to the last part of our conductors part 2, and that is conductors with cavities. So we have conductors with cavities. In case you don't know, cavities mean hollow spaces inside some volume. So this yellow thing, as you can see, is a conductor, and it has a hollow space inside, and that is the cavity. What happens if we start with a cavity and if we place a charge inside the cavity? So as we place charge inside a cavity, by any means, the field lines will start to emerge from the charge, and it will cross the conducting surface, the yellow surface, and then it will tend to move into infinity. This is what happens initially. But we know that a conductor is a conductor. The property of a conductor is that it has a lot of free electrons. So we will have positive charges on the outer surface of the conductor, or let me show it here, positive charges on the outer surface of the conductor. And negative charges on the inner surface of the cavity. And what is going to happen due to these charges? Due to these charges, there will be an induced field, positive to negative, as you can see, the induced field from positive to negative. And that field, this field is what we call as induced field, and this field is what we call as the original field E naught. And what is going to happen after that is this, simply this, that within the yellow region, the conducting region, let me move this up. Okay, so I need to move this up. Come on. In the yellow region, I have to draw this, which we call as the conducting region. Okay, so we have, right, in the yellow region, the field is going to be 0. The field is going to be 0 in the yellow region, because the yellow region is basically conductors. And what will happen due to field in other regions? In other regions, first of all, let's consider the distribution of charges. There was plus q, and there was a negative charge here, if you might remember, and there was a positive charge here, if you might remember. Both these red positive and negative charges were due to induction in conductors. So first of all, the field lines start from the positive green charge and end at 90 degrees at the negative charge, all of them at 90 degrees, because they are terminating on the surface of the conductor, so they will terminate at 90 degrees. And then there is a discontinuity. The discontinuity is in this region, of course. There is a discontinuity, no field inside the region. And then again you have fields coming out of the surface of the conductor, and all at what angles? 90 degrees. And this can be very well understood also by Gauss theorem. Let me draw a Gaussian surface here. This Gaussian surface, you might be thinking, where am I drawing this Gaussian surface? Although it's clearly evident from the diagram, but this Gaussian surface is just outside the cavity, or we can say just inside the yellow region. So this is your Gaussian surface. If you draw the Gaussian surface here and you tend to apply Gauss theorem, you will have E into 4 pi r squared is equals to q enclosed by epsilon naught. So this is your Gauss theorem. Now, as to the left part of the equation, we know that in the yellow region the field is 0. So if in the yellow region the field is 0, so the left part of the equation becomes equals to 0. And if the left part becomes equals to 0, q enclosed becomes equals to 0. And you can see that it is definitely 0. How can you say that? Inside the cavity there is a charge plus q, and then there is a surrounding charge minus q, same magnitude. So this is minus q, and then there is plus q here. So within the Gaussian surfaces you have two charges, plus q and minus q, both are equal in magnitude, and hence the net enclosed charge is equals to 0, and that is something that we can understand from the Gauss theorem. So this is the same conductor that we were discussing about. Initially we provided the conductor with a green charge plus q, then we got a red charge due to induction minus q inside the inner surface of the cavity, and since the conductor was electrically neutral, we get another charge plus q. I'll write it here. We'll get another charge plus q on the surface of the conductor. Now the first question is quite simple, and that is, what is the field at point P? And we know that field at point P will be due to three separate charges. Now let me name the charges. The charge on the outer surface will be called as C1. The green charge at the center of the cavity will be called as C2. And the charge here at the inner surface of the cavity will be called as C3. And the blue dot that you are looking at is basically the center of the spherical conductor. So let me call this as point O. Right? Now we know that electric field at point P will be electric field due to charge C1, of course, plus the electric field due to charge C2, of course, plus the electric field due to charge C3, of course. It will be due to three charges, due to C1, due to C2, due to C3, right? Now we will take each one of them individually, but before we start taking any one of them, I want you to understand a very simple concept. And this concept is not from conductors, it's from way back, Coulomb's law. If you have a uniformly spherical surface, charged, hollow sphere, I'm not saying that it is a conductor, I'm talking about a general formula. Field at a point P outside at a distance r is simply equals to kq upon r square, and field at a point P inside is equals to 0. You must remember that. That was the thing that we had discussed, that field at point P outside was kq by r squared, field at point P inside was 0. And there was a shortcut to remember this. The shortcut was very simple, that if you are taking any point outside, you will consider entire sphere as a point charge. So taking that into account, and now deleting it because we are practically running out of space here. Alright, so okay, it won't be of much help because they have a circle. Okay, no problem. So okay, so electric field, back to our situation, electric field due to C1 will be given as kq upon r squared, where r is the distance of the blue line, and the direction of the field will be obviously along the blue line, no denying that. This is the electric field due to C1. Let me write that in white. This is the electric field due to C1, right? Now second comes electric field due to C2, and you must know that C2 is a point charge. So electric field due to a point charge is very well known. So electric field due to C2, I will not discuss point charge here, is going to be kq upon r dash squared. R dash is the length of the green line, as you can see, and the direction of the field is away from the green line, like this. And comes the final and the most important part, the electric field due to C3. Now you must remember that C3 is a spherical distribution of the cavity. The charge is distributed on the cavity like a hollow sphere. I am repeating it again. The charge is distributed, C3 charge is distributed on the surface of the cavity like a hollow sphere, just like a hollow sphere, and we want to find out the field at a point outside. So for a hollow sphere and the point is outside, what do we consider? we consider that the hollow sphere is itself a point charge. So the field at C3 is going to be kq upon r dash squared, and the direction is going to be the opposite of C2. So this will be your field due to C3. And as you will see, the field due to C2 and C3, let me mark this. This was the field due to C2. The field due to C2 and C3 are basically equal in magnitudes. As you can see, they are equal in magnitudes and opposite in directions. So they will simply get cancelled out. So finally we have electric field at point P is simply due to the charge on the surface, that is kq upon r squared, and that is along the blue line. Now we are back at the question again, and this time I don't want to find out the field, I want to find out the potential at point P. Again we know that potential at point P is going to be the potential due to C1 plus the potential due to C2 plus the potential due to C3. Potentials due to three objects, three different types of charges. And again the principle of hollow spheres works in here. Let me draw this here. So if you have a hollow sphere and if you want to find out the potential at a certain point P, and the hollow sphere charge is q, radius is r, the potential at point P outside point is kq by r, and the potential at inside point, let's say this point, is kq, is k capital Q by capital R, where capital R is obviously the radius of the sphere. So these two potentials is something that we already know from the previous cases, so we are not going to fall into that, and we already know that, right? We already know from the formula for fields and potentials. So we are back here, potential at point P equals to potential due to C1. So we know that point P is outside of the sphere, the largest sphere, outside of C1. So we will simply write kq upon r, where r is the distance from the center of the sphere to the point P. Next question, plus C2 is a point charge, we all know that. And what is the potential due to a point charge? Potential due to a point charge is very simply kq upon r dash, plus C3 is a charge distribution in a hollow sphere, we also know that. And for an outside point P, hollow sphere simply acts as a point charge, we know that. So the potential is that we are going to write is this, so minus kq upon r dash, and you will see that the last two terms get cancelled out, and the potential at P simply becomes equals to kq by r. Now we are going to discuss potential at a point inside the conductor. So let's take up a point inside the conductor. We will take a point, let's say S inside the conductor. The point S inside the conductor. So we are going to find out V at S. Again V at S will be equals to V due to C1 plus V due to C2 plus V due to C3. Now we'll keep solving one by one. Now, what is C1? You know what is C1? C1 is the outer charge. You can see here C1 is the outer charge. For an outer charge, and S is an inside point, we do remember outer charge, inside point, the potential is constant, and let's say the radius of this thing here is r. The potential due to C1, will be given as kq upon r. That's it, inside point. And then we will have potential due to C2. You can see that C2 is a point charge. So let's say this distance is some x, let's say. The potential due to C2 will be given as kq upon x. Likewise, we can have potential due to C3. For you can see that C3 is a hollow sphere of charge and S is the outside point. So for any hollow sphere of charge, outside point is taken as a point charge. So minus kq upon x. And if you add all these three things, this is the first thing, this is the second thing, this is the third thing, you will see again that these two things get cancelled out, and the potential at point S simply becomes equals to kq by r, capital R. The potential at point S becomes equals to kq by capital. We are back to the same system again. There was a charge q at the center, as you can see. There's an induced charge minus q on the inner surface of the cavity, and then an induced charge plus q on the outer surface of the conductor. Now we want to find out the potential at point M. You can see the point M is inside the cavity, any general point inside the cavity. And let me first understand some basics here. Let's try to first understand some basics here. This is the center of the cavity. This was O, if you might remember, and this radius of the conductor was center of the conductor, I'm sorry, and the radius of the conductor was R. And let's give this cavity some radius. So let's say that this cavity has a radius A. Now we want to find out the potential at point M. Again, we know that will be equals to C1 plus potential due to C2 plus potential due to C3. This was C1. This was, I'm not drawing it, this was C2, the center charge, center of the cavity charge was C2, and the inner surface of the cavity charge was C3, that I can draw. So this is C3. Okay, so let's start one by one. What is the potential due to C1? C1 means the outer charge. Now we have an outer charge and M is an inside point. Can you see? This is an outer charge, M is an inside point. Potential due to an outer charge at the inside point is constant, remember? So the potential due to C1 becomes equals to, let me write this, potential due to C1 becomes equals to kq upon capital R, that is constant. Now potential due to C2 becomes equals to, again let's have a look at C2. We know that what is C2. C2 is a point charge, and let's say this is some distance. Let's mark the distance. Let's say this is some distance y. Okay, so potential due to a point charge is always given as kq upon the distance, so this time kq upon y. Potential due to C3, again what is C3? C3 is a hollow sphere of charge that is inside the cavity. And with respect to point M, how will you compare? We will say that this is a hollow spherical shell and M is an inside point. So again, potential at an inside point, do you remember? It is constant, so kq upon the radius, and what is the radius? The radius is A. And there is a negative sign because the charge on the surface of the cavity is negative. So what is the total potential that we are going to have? The total potential that we are going to have is kq by R plus kq by y minus kq by A. This is the total potential. If we want to look at the field at point M, this is very interesting to see. We will do it using the formula E equals to minus dV by dr. Field at any point is basically the rate of change of potential with respect to distance. And the potential, as you can see, is this is the potential. And we have to differentiate this potential with respect to distance. So what happens when we differentiate the first term? We can see that the first term is a constant. Why it is a constant? Because the radius R is constant. We will also see that the third term is also constant, because A is constant. Only the term y here is variable. only the term y here is variable. So when you will differentiate it, you will differentiate it with respect to y minus dv by dy, and that will become equals to kq upon y squared. And as you can see, the potential at the field at point M is not due to the surrounding charge, is not even due to the cavity surface charge. The field at point M is only due to the charge at the center, and that is kq upon y squared, where y is the distance. So we have a conductor here, and to make the situation more difficult, we have taken two cavities. You can see there's a left cavity here which has a radius A. There's a right cavity here which has a radius B. This cavity, the left one, has a charge at its center Q1, the right one has a charge at its center Q2, and the conductor has a charge capital Q on its surface. So first, let's try to understand the distribution of charges. If we draw a Gaussian surface here, we know that from the previous endeavors that the field will be 0, the flux will be 0, and the charge enclosed will be 0. If the charge enclosed is 0, then it becomes for sure that there must be a negative charge minus q1 appearing on the inner surface. Likewise, there will be also a negative charge minus q2 appearing on this inner surface of the second cavity. And since the conductor is electrically neutral, two charges plus q1 and plus q2 will be appearing on the outer surface of the conductor. And this is your new set of charge distributions. Now we want to find out field potential at some points, and let's say we have to find out field at point, let's say this is point P. And now I'm going to be fast here. The distance between P, let me draw it in different color, the distance between point P and the center of the conductor is x. Now we know that field at point P will only be due to this charge. Why this charge? Because the field due to this charge and this charge will get cancelled out. If you don't understand, please rewind the video a bit and then you will understand again. The field due to this charge and this charge will again get cancelled out. So the field at point P is only due to these charges on the surface. So the field at point P very simply becomes equals to k q plus q1 plus q2 divided by x squared. That is the field at point P. Likewise, potential at point P, again, as I will like to tell you, and again if you have missed out, please rewind the video a bit. The potential at point P due to these two charges plus q1 minus q1 will get cancelled out. Due to plus q2 and minus q2 will get cancelled out. The only potential that remains is due to this charge. So potential at point P will be very easily given as k q plus q1 plus q2 divided by x. These are your fields and potentials at point P. Now let's take a certain point here, let's say Q, and this has a distance x. We'll very easily know that field at point Q is equals to 0, simply 0, because field in any conductor is 0. The yellow material is the conducting material, the field inside the conducting material will be 0. For the potential at point Q, we will have a lot of things to consider here, but let's start working on it. First, the potential due to an outside charge. You see, this is an outside distribution and the point Q is an inside point. So we know that the potential due to this is going to be constant, that is k q plus q1 plus q2 divided by r, right? Now the potentials due to this will be k q1 upon, let's say, some distance x dash. So k q1 upon x dash, I am not writing it because I'll tell you it will get cancelled out. And why it will get cancelled out? it will get cancelled out due to this minus q1. Minus q1 is like a hollow sphere of charge, and this is an outside point. So for an outside point, a hollow sphere of charge is always taken as a point charge. So minus q1 and plus q1 are basically point charges for this point q. So the potential, combined potential due to the cavity 1 charges, let me call this cavity as cavity 1 and let me call this cavity as cavity 2. So the combined potential due to cavity 1 charges is 0, and likewise the combined potential due to cavity 2 charges will also be equals to 0. Okay, so this is our conductor once again, and if you haven't understood the charge distribution, please go back, rewind the video and see it again to understand it properly. But for now, I'll tell you this. The green charges Q1, Q2 and capital Q were the original charges that were given to the conductors. The red charges were the induced charges that were induced due to the conducting material. And we want to find out the field at a point M. Field at point M and potential at point M. This point M is obviously in cavity 1 and it is at a distance y from the center of the center charge Q1. So field at M simply becomes equals to k Q1 upon y squared. And why is that so? I'll discuss with you at the end of the topic. But for now, you will take the field as it is. Potential at point M will be due to all charges, obviously. So the potential at point M due to point charge Q1 will be equals to k Q1 upon y. Due to charge minus Q1, it's very important to see that minus Q1 is basically the charge on the surface. So it is a hollow sphere of charge. And due to a hollow sphere of charge and the point is an inside point, so when we consider a hollow sphere of charge and an inside point, potential will become equals to minus k Q1 by A. The potential is constant. Now comes the charge that is outside this charge. We know that the radius of the sphere is capital R. And again, this is an outside charge distributed on the outer surface, and M is an inside point. So the potential due to the outside charge at an inside point obviously will be equals to k capital Q plus Q1 plus Q2 divided by capital R, which is a constant value again. And the last point is the potential due to these two charges, that is minus Q2 and plus Q2. And if you do remember that this is a spherical distribution of charge, minus Q2 and plus Q2 is a point charge and M is an outside point. So when we are talking about outside point, the spherical distribution becomes a point charge. So Q2 minus Q2, the red minus Q2 will be taken as a point charge, as well as the green minus Q2, that itself is a point charge. And if you combine the 2 point charges, the net charge becomes equals to 0. So due to these two charges, the potential at point M will be equals to 0. So this is your definition of potential here, and that is the basic understanding of the potential. So at point M, the potential is due to all charges, no denying that, due to charge Q1, that is k Q1 by y, due to negative Q1, that is minus k Q1 by A, due to the induced charges on the surface and the original one on the surface, that is k Q1 plus Q2 by R, and due to these two charges, the potential at this point was 0 because this is an outside point and these two will be taken as point charges and they will cancel out. Now, if we want to find out the field from the potential, the field from the potential will be given as dV by dr. Now while differentiating, you must notice that these two terms are constants. This is a constant and this is a constant. And why are these two terms constant? Because A and capital R are constants. So if these two terms are constants, the differentiation of constants will be equals to 0. And the field will vary only on the basis of y, this y here. So the electric field can be written as minus dv by dr or minus dv by dy, and that will be equals to kq1 upon y squared. And that's what I was trying to explain it to you at this juncture, that the field at point M is only due to charge q1, and that is equals to kq1 upon y squared. This is the end of this lecture, and there is another lecture coming on the topic of conductors, that is conductors part 3, and in that we will discuss the field and potentials due to parallel plates and the concept of earthing. Till then, please revise it and have a good time.